Okay, so in this video, I'll show you how to do a couple of different half-life problems here. The first one being this one. It says the half-life of radium-226 is 1,600 years. And part A wants us to find out how much of a 1 kilogram sample has decay after 12,800 years. And then part B wants us to find the time that it would take for this sample to decay to 1 over 512 of the original amount. So here is a graph for radium-226. The starting amount here is 1 kilogram for this particular problem. As you can see here, it shows the half-life. So it'd be 1 kilogram, and it would be 0.5, and 0.5 divided by 2 would be 0.25, and then 0.25 divided again be 0.0125 or 1/8. So you keep dividing by 2 and by 2 by 2. Okay. So this is just a sample of this, what's going on here in the problem. All right, so let's go ahead and crack out part A. Part A asks us to find out how much has decay. So I underline has decay here for you because it's often found incorrectly. So let's go ahead and do it. The function to find the amount remains after a certain amount of time is n of t is equal to n naught divided by 2 to the exponent here. T being the time elapsed, t half being the half-life time. Okay. Well, in order to find how much has decay, you need to figure out how much is still left over after a certain amount of time. So you need to find n of t, and once you find n of t, you just subtract that from the starting amount. That will give you the answer of how much has decay. So I'm going to go ahead and find n of t here. I'm going to go ahead and plug in stuff I know. The starting amount for this particular problem and graph is 1 kilogram. The time elapsed is 12,800 years. The half-life time is given as 1,600 years. And then I'm just going to clean the exponent up a little bit. So 12,800 divided by 1,600 will leave me with an 8. So the numerator of 1 kilogram just gets carried down. So this would be 2 to the 8th power. So if you raise 2 to the 8th power in your calculator, you get a value of 256. And therefore now, at this point, you can leave it as 1 over 56 kilogram, or you can simplify the calculator in terms of decimal. So if you punch in 1 divided by 256, you'll get a value of 0.039 kilogram. However, you're not done yet, right? This is how much is still left over. This is how much is still present after 1,280 years. However, the question asks you how much has decay. And as I stated earlier, once you find out how much you still have, all you have to do, is really just do basic math here. To find out how much has decay, you would take the starting amount, subtract how much you still have, and that will tell you how much has been lost. All right, so the starting amount here is 1 kilogram. The remaining amount we just found, n of t, is 0.0039 kilogram. So this is how much you started with. This is how much you still have left over. So therefore, when you take the difference, it tells you how much you've lost or spent. Okay, so the amount that has decay is indeed 0.9961 kilogram, and that is our answer for part A. So be careful with the wording such as how much remains. If it asks you how much remains, you would have been done with this 0.0039. If it asks you how much has decay, you would just have to take it a step farther and subtract it from the original amount, whatever the original amount is. It's just for this one, it happens to be 1 kilogram. Okay. All right, let's do part B. Part B asks you how long it will take for the sample to decay to 1 over 512th of the original amount. As you can see in the graph here, it kind of leads you here. It starts with 1, and 1/2, and 1/4, 1/8. So we just keep dividing by 2. So until you get to 512 in the denominator. But I'll show you how to do this properly. So to start, I'm just going to go ahead and use the other function for half-life, hopefully just to show you how to play with these different variations of half-life. N of t is equal to the original amount, e to the negative k t. Keep in mind that k is 0.693 divided by time of the half-life, or ln of 1/2 divided by t of half-life. So hopefully you've seen the other videos or you're exposed to this content already. All right. So here, what is n of t? N of t is simply 1 over 512, whatever this fraction is of the original amount. On the right side, all I did was I substitute out k for 0.693 divided by the half-life time, which is given to us here in the wording. It says this particular radium 226 splits every 1,600 years. Okay, so that's how much the half-life time is. And naught cancels out on both sides, and then the only thing left on the left side is 1 over 512, and then the only thing left on the right side is e to the negative 0.693 divided by 600 and then times t. T is what we're trying to find here, because the question asks us how long will it take for this particular phenomenon to occur. So here, in order to get T down, because right now T is in the exponent, okay, and you have E. So to undo E, you need to introduce natural log. So natural log on the left side, natural log on the right side, natural log ln, and E cancels out, so I didn't carry that down. Once again, ln on the right side, and E natural will cancel itself out, which allows us to bring the exponent here down to the main function, which allows us to now solve for T. So on your calculator, if you want, you can simplify ln of 1 over 500. You'll get about negative 6.238. On the right side, I kept it the same. So at this point, it's up to you in terms of algebra. You can simplify this fraction, and then from there, you can divide both sides by this division. Or I'm just going to go ahead and multiply both sides by 1,600 years, and at the same time, divide by 0.693. So again, it's entirely up to you how you want to simplify this statement. So like I said, I will go ahead and multiply both sides by 1,600. At the same time, divide by 0.693. So if you do this correctly, the negative signs will cancel out, and then it will leave you with about 14,402 years. So that is the answer for part B. So it'll take about 14,402 years for this particular 1 kilogram sample to reduce down to 1 over 512th of its original amount. Okay. All right, let's go ahead and do the second problem of this video. Here, it says after 1 year, 80% of the initial amount of a radioactive substance remains. So you notice here the initial amount is not given. The time elapsed is given as 1 year, and then what percent, the percent of the original amount. So if you listen to the first video, the initial amount doesn't really quite matter for these types of problems, only because, especially when it's given percentages and fractions. Okay, let's do part A. Here it says what is the half-life of the substance, and then part B says how many half-life have passed until only about 3.125% of the radioactive sample is left over. Okay, let's do part A. To find the half-life time, I'm just going to go ahead and start with this other variation of half-life. N of t is equal to n naught, once again divided by 2 raised to the time elapsed divided by t of 1/2. Well, in order to get the half-life time, I need to go ahead and plug stuff in that I know. What is n of t? N of t is 80% of the original amount. How do you express that? 80% needs to be converted to decimal. That's where the 0.8 comes from. 80% of what? Of the original amount, whatever n naught is. On the right side, the whole function just carried down because nothing has changed. So I made a note for you here. Make sure to convert percent to decimal. 80% is 0.8. So to convert 80% to decimal, so you have to take 80% divided by 100%. So 80 over 100 is 0.8, and that's where the 0.8 came from. And naught appears on both sides, you can just cross that out. So from here to find t1/2, you can just go ahead and manipulate the function in order to get t1/2. I'm going to go ahead and move this bottom right with the exponent to the left, and then at the same time move 0.8 down. So I'm going to do a little switcheroo here real quick. Okay. Once again, I want to move the bottom right up to the top left, at the same time move the 0.8 down. That's because I need to solve for t half-life. Well, t half-life right here is in the exponent. So from here, I can just plug in values that I know. Well, t, what is t? T is 1 year. The problem says so. It says after 1 year. So how much time has elapsed? T is 1 year. Well, how do I get this t1/2 to come down to the main function? I would have to log both sides. So I'm going to do log 2. And then what I do on one side, I got to do on both sides. 1 divided by 0.8 is 1.25. So I'm going to log 2. And then that brings the exponent down. So if you clean this up a little bit, okay, log 2 times 1 is 0.301. And then the t1/2 here remains because I haven't touched it yet. And then log 1.25 is 0.097. So how do I solve for this half-life time? Well, it's in the denominator right now. So to solve for stuff that's in the denominator, you have to get it to the numerator. So I'm just going to multiply both sides by t1/2, or literally I'm just going to move this t1/2 to the top right. At the same time, move this 0.097 down to the bottom left in order to get t1/2 to the numerator. So once you do that, really all you have to do is simplify your work. 0.301 divided by 0.097. That'll tell us that the half-life of this particular substance is 3.1 years. Okay, so after every 3.1 year, it splits So after another 3.1 year, it splits again. After another 3.1 years, it splits again. So that is the half-life time for this particular substance based on what's given to us. Okay. Now let's do part B. I'll show you how to do part B a couple of different ways. Hopefully you like the second strategy better. But the first one is quote unquote formal. It says how many half-lives have passed until only 3.125% is left over. So I'm gonna start with the same starting point here, and then really the only thing difference here is I'm just gonna convert 3.125% once again into decimal just by dividing by 100. Dividing by 100 shifts the decimal place 2 space to the left, so percent is now 0.03125 of the original amount. The original amount cancels out. So if you kept up with part A here, it's pretty tedious. It's essentially the same work, but except for 80%, it is now replaced with 3.125%. Well, once again, I'm just gonna go ahead and clean this up, and then I want to go ahead and move the bottom bottom right to the top left, and then I want to divide both sides by 0.03125. So just get t by itself. But once again, in this particular problem, I'm solving for t because in order to figure out how many cycles have passed, I need to figure out how much time have passed, because I know that each cycle takes 3.1 years, which I already found in part A. So this is where the 0.31 years came from. That's because I already found the t1 half in part A. Okay, so this one I need to find what t is. Well, to find t, once again I want to use the same strategy. I want to log both sides. Logging both sides brings down the t. So on the right side, if you do 1 divided by 0.03125, you get 32. So therefore you would do log 32 and then log 2 on the left side and then log 32 on the right side. So if you do that correctly, if you do log 2 divided by 3.1, you'll get 0.0971t because the t is on the top. And then if you do log 32, you get 1.505. Now at this point, to solve for t, you would just divide both sides by 0.0971, which is what I did here. So if you take your calculator and you do 1.505 divided by 0.0971, you'll get that about 15.5 years has elapsed. Okay, so how much time has elapsed is 15.5 years, but the question didn't ask for the amount of time that has elapsed. It asked for how many half-lives. Well, from here, all you have to do is do this little extra step. You already found how much time has gone by, which is 15.5, but it asks for a number of half-lives. So just take the number of years that have gone by, divided by the number of years that it would take for each half-life to occur. So each half-life takes 3.1 years, but in this case, it'd be 15.5 years has elapsed. So 15.5 divided by 3.1 tells us that it has split 5 times. Okay, so it would split at 3.1 years. And then another 3.1 years has gone by, it'll split again. Another 3.1 year, it'll split again. Another 3.1 year, it'll split again. So eventually, in order to get to about 3.125%, it needs to split 5 times. So there's 5 cycles. That is our answer. Okay. All right. The other way I like this second strategy, I like a little better. That's because, well, I can just rewrite this whole entire function as n naught divided by 2 to the c power. C here stands for the number of cycles, which is what I'm trying to find, right? Part B is a little different. It says how many half-lives have passed. It didn't ask for the number of years. It asked for the number of half-lives. So instead of writing all this t divided by t1 half, I'm just going to simplify it. The exponent is just the number of cycles, because t divided by the number of years for each half-life is indeed c, which is what I did down here. Okay, so in the second strategy, that was my last step. However, I want to go ahead and make that my first step in my work here. So I want to say that n of t is equal to n naught divided by 2c. C here stands for the number of half-lives or cycles that have elapsed. So here, well, the left side stays the same. What is n of t? N of t is still 0.03125 of the original amount, whatever that is. As you can see, n naught on both sides cancels out again. So here I'm going to clean it up. Canceling out n naught reduces that term to just a 1. On the left side, I just carry down the percentage and decimal form here. So really the only thing, as you can see here, is just a c. So I want to go ahead and move 2c up to the top left. I want to move this 0.03125 to the bottom right and do a little quick switcheroo. And then c here is the exponent. So to get c down where we can solve for it, we have to log both sides. Logging both sides bring the c down. So if you do 1 divided by 0.03125, you get 32 again, just like I did over here in the middle section. And then here, log 2. times c is equal to log 32. Well, to get c by itself, you just divide log of 2 on both sides. So that's what I did. So I just moved log of 2 to the bottom right. So you punch log 32 divided by, log of 32 divided by log 2 on your calculator. That will give you a 5. So therefore, it takes 5 cycles to reduce the original percent or 100% down to just 3.125%. Okay. All right. I hope that helps. Stay nerdy. Don't be whack.